The next talk is by Sarah Conrad. She's a PhD student from Heidelberg University, and she's giving a foundation talk about how the universe works.
Thank you. Yeah, hello everybody. I'm really amazed how great the interest in this community is for science. This is really, really awesome. And I'm really happy to be here today to talk to you about how to reverse engineer the universe. And by that, we will see that we have to explore the very, very dark sides of the universe. So imagine you are on a very clear night outside. You observe the stars, and maybe you wonder, what is out there? There are all these tiny little stars. Maybe you have images from colorful nebulae in your mind, and you wonder, what else is out there? And how far is all that? And where does this all come from? So how people imagined the world to work in former times is depicted here, and the caption says, a missionary of the Middle Ages tell that he had found the point where the sky and the earth touch. So people believe that there is this curtain in the sky, and stars are pinned on this curtain, and they were so curious and wanted to know the secrets of how the world works, and wanted to look behind the curtain and see the machinery, what's going on there. Of course, today we know that the sky is not a curtain with stars pinned on them, but we know that we live, our sun lives in the Milky Way galaxy, and today we know that the sun is a relatively average star among all the other stars we see. And in case you lost track where you are now, so you are here. Yes, so at the beginning of the 20th century, people indeed believed that the Milky Way galaxy is made the whole universe. So the whole universe consists of our Milky Way galaxy, and everything we observe in the sky is within our own galaxy. So you see, the worldview got a little bit larger. So we went from only our own little planet to a whole galaxy. This is what we observed. But people also wanted to know how space-time works. So the stuff our Milky Way galaxy is embedded in. And how could we investigate this question without him, Albert Einstein? In 1950, he found the general theory of relativity. And this theory made the essentials for our current understanding what space-time is and how it works. So I will introduce to you now the most complicated equation in this whole talk, but this is really the essentials. The essentials of general relativity is one simple set of equations. On the left-hand side, they show the dynamics of space-time. So the dynamics of space-time is equal to the energy and the momentum content of our universe. What does this mean? In case our universe was empty, the dynamics would vanish. Nothing would happen. Space-time would just be as it is. But as soon as we fill our universe with stuff, with matter, with radiation, the dynamics of space-time will come into play, and space-time will not stay as it is. The space will expand or contract, will curve, and matter will begin to flow and to go into movement. This sounded really very strange to people at that time, a universe that changes its size. And people don't wanted that. This was really something people didn't want. So Albert Einstein introduced a further factor in his equations, this lambda factor, to cancel out the effect of the matter and the radiation in our universe in order to make it static. So nice and smooth as everything should be. This further factor was allowed by the equations, but the nature of this factor was really mysterious. Is it an unknown energy or a property of space-time? We will see. This is how our current understanding of space-time developed. But what about our understanding of our surrounding? As I told you, at that time people believed that the Milky Way was all our universe consisted of. We were not able to see much further, and what we know today are other galaxies just appeared as spiral nebula in the sky, because individual stars could not be resolved. Now, Henrietta Swan-Leavitt was a woman who worked at the Harvard Observatory, and she investigated stars in the large and the small Magellanic Cloud. Now we know that these clouds are tiny galaxies that accompany our own Milky Way galaxy. And at the time she worked there, she found out that we see already individual stars in these clouds, and she observed stars that vary in their brightness on a range of days. So they pulsate, they increase in magnitude and decrease in magnitude. And what she also saw was that the faster this pulsation works, the brighter these stars are. And with this, it was possible for the first time to search for these Cepheid variable stars, measure their pulsation. Now, since we know the relation between the pulsation of stars and their brightness, we observe them in the sky, we can infer the distance of these stars. And this is what Edwin Hubble did. So he found in the Andromeda Nebula and the Triangle Nebula these Cepheid stars. And he used this method of inferring the distance. And what he found was that these nebula must be farther away than all the stars that we can see. So for the first time it was clear that there are objects outside our own galaxy that are huge. And with that, even our own galaxy was not a special place anymore, just a place like many others in the universe. And our view from the local neighborhood evolved. Our Milky Way galaxy here, so again, you are here, in case you lost track. And the Andromeda galaxy turned out, which we previously believed was only another nebula in our own galaxy, maybe tiny, is even larger than our own galaxy. But the physicists wouldn't be satisfied with only knowing where stuff is. Physicists also want to know how the stuff moves, why it moves, and all the machinery behind that. And now in order to determine how the stuff around us really works, let's make use of another effect you might know from acoustics, the Doppler effect. Imagine you standing on the street and a fast car is passing by. The sound the car makes while it's approaching you is different than the sound it makes when it's driving away from you. It's like, first it's high and then low. So what you see is that there's a change in frequency due to the relative movement of the car, and this leads to a change in pitch. Now the same is true for light. The physical reasons are a bit different, but the effect is the same. Imagine there's a star that's approaching you. Its light will be shifted to higher frequencies if it's approaching you. So you will observe a change in color. So the star would appear more blue. On the other way, if the star is moving away from you, it will appear more red. That's why we call this effect redshift or blue shift. Now, in order to determine the relative velocity of a star, with respect to you, it's not enough only to measure the frequency of the light, because you don't know what the real color of your star is. So for this, we make use of spectral lines. Spectral lines are fingerprints of individual chemical elements. Every element has a very special line feature absorption line feature in the spectrum. And when you observe a certain line configuration, you know which element this belongs to. And in principle, this line feature should always be at the same frequencies. But when a star moves towards us or away from us, also these lines are blue and redshifted. Which means by observing spectral lines from stars that moving close to us or farther away from us, we know the velocity with which they move. Okay, now we learned how to measure distances and how to measure velocities in the universe. And this was done by Fritz Zwicky. He was a Swiss astronomer and investigated the velocities of galaxies in galactic galaxy clusters. A galaxy cluster is a very huge object. It's a gravitationally bound object of individual galaxies. And what he did was, he was interested in, maybe they're like a mobile, they're moving around, staying together, and he measured the velocities. And what he found was really, really strange. These galaxies moved with speeds so high, such that it was unbelievable that these guys could stick together. Because the gravitational potential could not be so high from the mass we observed. I mean, we observed the brightness of these objects. We knew how many stars should be in there. And now they are moving with these speeds. Fritz Zwicky concluded that these galaxy clusters must be much, much heavier than we actually observe, than we actually think. And he first introduced the term dark matter for that. He believed that dark matter might be maybe gas or dust or maybe rocky material we just can't see because it doesn't glow. In later times, a more detailed analysis was done by Vera Rubin. She used the same principle, but she measured velocities of stars within certain galaxies. So now we have a galaxy, certain stars in there, and we measure the velocity with which the stars circle around the center of the galaxy. And by that, she measured this profile, which you see here. So on the x-axis, you see the distance from the center of the galaxy. On the y-axis, the speed. And the white curve is the measured speed of these galaxies. And as you see, at the center, it rises, and then it gets relatively flat. But again, from the mass we can observe in these galaxies, we would assume that in order to hold these galaxies together, the velocity should be much, much smaller. And at that time, it was already possible to infer the gas and dust content of these galaxies. So it couldn't be dust or gas that's in these galaxies that leads to this excess in mass. So again, we observe that there must be more mass than we expected. So the hints for something like dark matter got more and more. But let's go back to our view of how the universe itself works. Now we have this mysterious of what's inside, but how does it work itself? Again, we go back to our well-known Edwin Hubble, and what he measured was, he looked at the galaxies in our surrounding, and he wanted to know with which movements are our surrounding galaxies moving with respect to us. And what he found was the now called Hubble law, that the farther away a galaxy is, the faster it moves away from us. So galaxies are fleeing from us. And this is a linear relationship. But what does this mean? Today we know that the universe expands. We call this Hubble expansion, and Hubble would be really, really unhappy about this expansion naming after him because he never believed that space itself expands. But okay, famous but wanted or not. But what does it mean that the universe expands? Does it mean that we are at the center of the galaxy and everything around us expands? No. The universe expands at every point. So let's assume we are at point A. And we observe a galaxy at point B moving away from us. Now, when we go to galaxy B, what would someone in galaxy B see? Galaxy B would also see that A is moving away, but galaxy B would also observe that anything else is also moving away. So the universe expands around every point. There is no center where the universe expands from. It expands from every point. And the first one who formalized this observation was Alexander Friedmann, who found the equations that describe these specific movement of our universe. He said the universe must be homogeneous and isotropic, meaning that it looks the same everywhere and in all directions. Regardless in which direction of the universe we look, it looks the same. Why should it be different at another point? But it changes in time, it expands. Which means that if we take a large amount of space today, we go back in time, this amount of space will shrink and shrink and shrink and become smaller and smaller. And by becoming smaller and smaller, it becomes, the matter inside becomes denser and denser and hotter and hotter. And if we go back in time up to some point, densities and temperatures are so high such that the universe becomes ionized. Which means that all the matter, the atomic nuclei, will not hold the electrons anymore by them, but electrons and atomic nuclei are moving freely around, not being bound to each other, which is depicted here on the left-hand side. But if we are in such a hot, dense plasma, what's happening with light? Light here are these yellow curves, and light scatters on free charges, which means that in this hot and dense plasma, so imagine you are sitting there, apart from the fact that you will be cooked, you could not see anything, because the light scatters everywhere and will not directly reach its aim. But at some point where the universe now expands, now we go forward in time, the universe cools, the nuclei catch the electrons, and the universe becomes transparent. And at that time, a huge amount of photons was released. And the cool thing is that we have a picture of this time. And this was one of the most famous pictures in cosmology we ever saw. And I want to share it with you. That it is. Thanks to these two guys, we have this picture, Penzias and Wilson. They were working on the Holmdel laboratory on a radio antenna. I wanted to measure something completely different and had always this noisy background in their antenna, and they wanted to get rid of it. They thought this might be pigeon poo or something else. They cleaned their antenna and anything. They couldn't find out until someday they met a physicist and they told him their problem, and he said, "What you measured is the first light from the universe." And for this, they got the Nobel Prize afterwards, and they got the Nobel Prize, and physicists got a new toy to play with. Because once you have a new measurement, okay, this is homogeneous and nice, and you laughed because of reasons. So physicists wanted to know, okay, is this really so homogeneous as we see it? And they did computations and computations. Today we see structures in the universe, so they might have been initially also when this radiation was released. So do we see reminiscence of these structures, of these initial structures in this radiation field? And they computed and computed and thought, okay, how much matter do we have in the universe? And they computed, okay, I guess so they guessed the fluctuations in this radiation field must be of the order of 100 Kelvin, which is really, really tiny. They started measuring and they found nothing. What was wrong? Did they do a mistake? In the 90s, the COBE satellite measured for the first time the fluctuations of this radiation field. And it turned out that the fluctuation amplitude was much, much less than expected. It was 100,000 Kelvin. And the only reason that these tiny fluctuations are so tiny is that a large amount of the matter at that time, when the cosmic microwave background, this radiation was released, did not interact with light. So here we have the proof that dark matter is indeed invisible. We will never be able to see it, to take a picture directly from it, because there's matter in our universe that does not emit photons, that does not interact with photons, that is so completely different than what we know. The cosmic microwave background nowadays is much more detailed, investigated, and these tiny fluctuations we see there, here measured by the Planck satellite a few years ago, serve as seeds for the big structures we see today. And if you're interested in how cosmic structures evolve from these fluctuations, I strongly recommend you, if you didn't have seen the talk on day 2 by Philip Bush, Simulating Universes, go there, have a look, and see how structures are formed from these fluctuations today. But what do we know now about our own universe? You know, we still wanted to reconstruct our own universe. At the very, very beginning, there was the Big Bang. So when we go back in time, compress anything, at some point we reach really the 0 point. This was the Big Bang. Then there was a brief period, we believe, of very, very fast expansion called inflation. Less than 400 years after the birth of the universe, we have this release of cosmic radiation, the cosmic microwave background I presented to you. Then the Dark Ages came, where no stars were at that time. Then stars, galaxies formed. And then a new epoch started, which was confirmed approximately 10 years ago, which was the accelerated expansion of the universe. You remember this cosmological constant factor Einstein introduced in his equations in order to make the universe static. Nowadays, we see that it's not there to make it static, but the effect of this constant is indeed to make the universe today accelerating. So Einstein invented, so to say, dark energy without knowing it. But today we know, okay, something in our universe is there to make the universe further and further expanding. Regular matter cannot do that. Regular matter contracts space, but cannot expand space. What do we know about the ingredients of the universe? Directly at the release of the cosmic radiation, we had very much dark matter, atoms, neutrinos, and photons played a big role. But with the expansion of the universe, their role became less and less important. And today we know that the density of the energy content of atoms make just 5% of our universe today. 27% is made up of dark matter. And the largest amount of energy in our universe is dark energy. What do we know about dark energy? We know that it is there. The universe accelerates. The other matter and radiation forms cannot be responsible for that. So something like dark energy must be here in order to serve for this accelerated expansion. We know that the energy density is really very homogeneous in space, so it does not form any structures like matter does. It may be constant in time. We have no hint today that the energy density of dark energy changes in time. So maybe it stays constant forever, then we have this cosmological constant, but physicists, of course, don't think, okay, maybe it's constant, so yeah, let's assume it's constant, but let's check that. And this will be checked in upcoming studies up to an accuracy of 10%. So in the next years, we will see, does dark matter, dark energy change its density in time or not? And anything else about dark energy is highly speculative. There are many different models that predict different things, but nothing known today. So this is all we know about dark energy for sure. Let's go back to dark matter. Maybe we get a bit more to know about that. What could dark matter be? Standard matter. Let's briefly recap what standard or normal matter is, or the matter we understand. Everybody knows what an atom is, I guess. So you have a nucleus that's positively charged. You have electrons moving around. Here's this, the quantum physicists are not here today. But you see what I mean. So in the core of these atoms, there are protons and neutrons, and every proton and neutron, again, is made of quarks, what we know today. Now, what are quarks? There are 6 kinds of known today. The up quark, down quark, the charm quark, the strange quark, the top quark, and the bottom quark. Physicists sometimes have humor, yes. Protons and neutrons are made up of up and down quarks. The other quarks are much heavier and not very stable, but they have been seen in the LHC and other colliders, for example. Then we have the leptons, electron, muon, tauon, and for every electron, muon, tauon, there is a neutrino. This is regular matter, or radiation in the neutrino case, and this is not dark matter. We know that. So we can rule that out. One thing at least we know. Okay, but now we know what it is not. What might it be? Maybe primordial black holes. So I told you that when the cosmic microwave radiation was released, there's matter, the dark matter, could not interact with the photons. A black hole does not emit photons, so it traps photons. So maybe we had at that time many, many black holes there. But the problem with this theory is, although it could lead to the observations we make today, that there are very, very few and very exotic cosmologies only that allow the formation of primordial black holes, because black holes must have been formed before atoms formed. And astrophysical observations allow only a very tiny range of masses for these primordial black holes. So primordial black holes are not excluded today, but not the likeliest ones. Maybe our particle model is not complete. So maybe there are particles in our that are not in the standard model. This is why we call this beyond the standard model particle physics, that are this dark matter. Maybe this is particles, just like we know, but a bit different. How could we detect them? So there's a certain class of dark matter particles, or model class of dark matter particles, called weakly interacting massive particles, or WIMPs, here just depicted as dark matter particle. And in case they go for the weak interactions, they could scatter with atomic nuclei. And we could see this scattering in large detectors. And this is what is done today. So people are looking for possible dark matter particles that are so different from what we know, but maybe they interact via the weak interaction. And this is the current status of different experiments. So the properties we want to know of our dark matter particle, if we detect it, is what mass does it have, and how likely is it to interact with our other particles, with our normal particles. So let's assume our galaxy is filled with dark matter particles, or WIMPs. We know what the density of this guy must be because we know the mass of our galaxy. So the heavier these WIMPs are, the fewer are they. So the number density is lower if the mass is high. This is one number we want to know. We want to know the mass and the size of these guys, or the probability to interact. And this is what these experiments shown here measure. So they want to know, okay, given a certain WIMP mass, because we don't know what the mass is, there's a plethora of models, so there's a huge parameter space to investigate, dependent on the WIMP mass, and assuming a given cross-section, would we detect this particle? Now, the continuous lines shown here are running experiments, so every line shows, given a certain mass, if the cross-section or the size of our particle is above the line, we would be able to detect it. If the size is below, meaning the interaction probability is low, we would not see it. The dotted lines are experiments that are under construction. And what you see here, relatively bad, but what you see here, the orange regions, so I distinguish the regions we already have. So in the lower regions of very, very tiny particles, if the WIMP would be very, very tiny, we couldn't distinguish them from neutrinos, so we are blind in this region. The red area are already running experiments. We know that WIMPs in this range are basically excluded. There were certain signals which are under discussion currently, it is a bit unclear. Did these experiments saw really something, or were these signals from other sources? And the dotted lines are experiments under construction or in planning, and the line, the blue, green, yellow line is one of the most forwarded experiment now, which would really go down up to the neutrino background. So if these experiments will run one day, and if there are WIMPs, we could possibly sometime detect this experiment will see it. But currently, everything we saw, it looked really, really bad. Okay, so this is if WIMPs interact with our normal material. But maybe there's another possibility. Maybe they don't interact with our normal material, but they interact with each other. So you have two dark matter particles, seen here. They interact. We say that they might annihilate because they maybe vanish and flow apart to different stuff. And there are many models that say, okay, in case we have this kind of model or that kind of model, there must be photons or neutrinos produced by that. And this smoking gun radiation, this indirect detection of dark matter, this could possibly be observed here. Now, the problem with this indirect detection is that the photons or neutrinos that are produced there are not necessarily very unique. So basically what you have to do is you have to observe the whole sky for all the radiation. You have to measure all the photons, all the neutrinos, know where they are coming from. Which means that just if you don't know why this photon comes here, what the source of this photon is, doesn't mean that dark matter is the reason for this radiation. So So identifying all the sources in the sky and really labeling all the stuff we measure here is of high effort. And I wanted really to mention here the talks from Joost Megindas on day 1, going deep under to watch the stars on neutrinos, and multi-messenger astronomy, the identification of cosmic radiation and neutrinos, which was by Annie on day 3. So there you see more of how this cosmic radiation can be measured, can be identified, and what might be, how we can go on. But currently this is really a really hard problem. Okay, unknown particles, maybe we are about to see what's going on there, but we are already relatively far. So maybe let's consider a completely different direction what dark matter might be. So maybe it's not a particle, maybe we will never see a particle that we assign to be part of not the standard model and being responsible for this dark matter we observe. So maybe our theory of gravity is just wrong. Maybe on large scales, or very large scales, the scales of a galaxy cluster, gravity just works differently than we think. So maybe Einstein was wrong. Now, in order to test this hypothesis, I will introduce you with a further physical effect, which is gravitational lensing. So I told you that matter or energy changes the shape of space-time, which means that if you have a huge and massive object, it will deform space-time, it will curve space-time such that if you have here this massive object and I shine light to you from behind, the light rays will be curved around this massive object. And this is what you see here. So you see here a photograph of the galaxy cluster Abell 2218, and these arcs you see are not mistakes in the picture or in the lens. No, these are due to the bending of light of this galaxy cluster. So these arcs you see are galaxies behind these galaxy clusters, and their light is bent around in space-time until it reaches us. Now the cool thing is with this method that we can, by analyzing the shape of these arcs, we can infer the mass of this galaxy cluster. So we have another independent method to determine the mass of a galaxy cluster apart from the velocities in its center. So you remember Fritz Zwicky, who measured the galaxy velocities? He inferred masses, and now we use gravitational lensing to infer the mass of a cluster. So we have two independent techniques, and let's see what comes out of that. This was applied to the bullet cluster. So the bullet cluster is a very massive cluster, and what you see here, the lines are lines of constant gravitation, so to say. And you see that there are two centers of gravity, implying that this bullet cluster has two components. So maybe it was first two clusters and they moved to each other, and here we see the centers of gravity. Now, in case gravity works different on large scales, we would expect that all the luminous mass, or the mass that we know, the atoms, the gas, would also be there, because only the strength changes. So we can look at the gas in these galaxy clusters also via another independent technique, not only by measuring the mass, but the gas that fills galaxy clusters. And the gas that galaxy clusters fills, the mass of this is much higher than the galaxies themselves. So this is really the massive part of known matter in galaxy clusters is very hot, and it emits X-ray radiation, which means we can observe this gas in X-rays. We measure the mass of the galaxy cluster with gravitational lensing. We measure the location of the gas in the X-rays, and what we see is that the gas is not where the centers of gravity is. Here you see the bright regions are denser and hotter regions of gas, so the gas is delocated from the center of gravity, implying that gravity is not just scaled, the gravity from the gas is not just scaled on larger scales, but they are really different kinds of mass there. One, the hot gas, which you see more in the center, and more outside, this must be the mass of our dark matter. And the reason why the gas and the dark matter are delocalized in this case is because we have here indeed two galaxy clusters that moved through each other. The gas felt the pressure from each other, heated up. You see these wings going to the middle, so it flew through each other, but heated up and was slowed down, whereas dark matter, which does not interact in that sense, just flew through each other without really noticing. This observation killed a huge amount of modified gravity models, which assumed just the different strength of gravity on larger scales. So modification of gravity. There are still modified gravity models left, so different kinds of gravitational theories, apart from the general theory of relativity, which are possible. But let me tell you that one further observation also killed a lot of these models, was that the neutron-star merger in the past time, maybe you heard about that since we have this gravitational wave detector, there was a neutron-star merger detected, and for the first time, this was really a huge discovery in multi-messenger astronomy, because this neutron-star merger was observed via gravitational waves and via photons and via neutrinos. So what we saw was that the speed of the gravity of the gravitational waves that reached us and the speed of the light emitted from this neutron star merger was the same. And this was also something that is not predicted from certain modified gravity theories. So there were many modified gravity theories who predicted that the speed of light is different from the speed of gravity. But now we know the speed of gravity is the same as the speed of light, which also improved our knowledge about gravity itself and is a further reason for general relativity. So these are the most common models or ideas we have what dark matter might be. Maybe it is something completely different, something we cannot imagine of. But this is hard to detect, something we cannot know. What do I want you to take home? We saw how the universe, our view of the universe evolved, especially in the past century. We know that today only 5% of the energy content of our universe is known to us. These are the atoms which make up the gases, the dust, the stars, the earth, us. This is only 5%. 5% of the stuff in our universe is something we can possibly ever see. The other stuff we will never see in the visual regime. 27% of the energy content of our universe must be something like dark matter. An excess in mass we cannot explain currently with different models. Maybe it is a particle. We don't know. And the largest majority of the energy content in our universe is this strange thing called dark energy. That stuff that makes our universe expanding in an accelerated way. And since we have no other reason to believe differently, the future of our universe will be the cold death. Everything will expand farther and farther. It will become colder and colder because it gets less dense and less dense. And maybe this goes up to infinity. Maybe there's something else coming in we don't see yet, but we don't know. All we know is that these three components are nowadays the most important components, and that 95% of the stuff is literally in the dark. But we will know better in the future. So stay tuned and explore the dark. Thank you.
As far as I know, there are some questions from the internet. If you have some questions, to stand up and go to the microphones that are over there, and over this, I think too. But first, from the internet, similar.
Thank you. What do you think about the theory of higher dimensions, like string theory forms, such as D-brain or P-brain?
Yeah, so string theory has a hard time to make predictions that are actually testable. And I guess this is at least for me, this is really one of the most important things to follow a theory. It is absolutely worth developing these theories because we learn a lot from them, but now, at least now, I don't think that they are of much relevance for us now.
And the next one.
Has there been research about effect of inhomogeneities on the accelerating expansion of the universe, thinking about the big voids that we observe in the cosmic structure?
So, what effect, sorry, where are you?
Okay. This was from the internet.
Oh, this was from the internet. Could you repeat the question, please?
Yes, sure. Has there been research about effects of inhomogeneities on the accelerating expansion of the universe?
So there is definitely research on how inhomogeneities, especially voids, affect the expansion of the universe itself. And it has been shown that only voids cannot be responsible for the accelerated expansion. So only with these inhomogeneities you don't arrive at the cosmology we observe.
Thank you, Internet. Microphone number 2, please.
When you show the picture of baby universe, very cute, by the way.
Thank you.
Why does it have an elliptic shape?
Oh yeah, thank you. Good question. I forgot to mention that. So this is a whole world view, so to say. It's like a map of the Earth, but projected to the sky. So when you have a map of the Earth, it's also an elliptic shape. So it's a whole world, whole sky view, so to say.
Thank you. So, microphone number 1, please, and speak like me directly into the mic because someone else can hear you then.
How likely or unlikely do you think it is that there's maybe a fault in the measurements we did which indicate to us that there must be something like dark matter, like that rotation of the galaxies? How sure it is that all those measurements are correct and there must be something we don't know of?
All of what is correct?
Measurements which indicate that there must be dark matter, like the rotation of the galaxy.
They are nowadays, we live, so this is a term that is very often used on cosmological conferences. We live in an age of high precision cosmology, which means that the values we can measure nowadays are really, really very, very precise. Yes.
Mic number 3, please.
You said for the dark energy that there is some new information about the temporal structure that we get. Can you elaborate a bit on what experiments or measurements will give information there?
Yes, so Euclid and LSST, so the large-scale sky survey, will give at least up to some accuracy hints. So if there is a strong temporal change in the dark energy content density in our universe, we will get a hint for that. If it's very weak, of course, we cannot see that then. But in the next years, we will get more information on that, yes.
We increment to number 4.
Hi. You said that the measured energy fluctuation in the cosmic microwave background was much smaller than the expected fluctuation.
Yes.
Can you, and the factor was around 1,000 times smaller. Can you give me a reason for this large factor?
Yes, so the reason is that we have only a fifth of the matter that could be responsible for these fluctuations does indeed interact directly with the photons, which means that the fluctuations you see in this radiation background follows the fluctuations of the matter, but only of the matter it interacts with. And if it interacts only with a tiny fraction of the matter, the amplitude of these fluctuations will be much smaller than if it would interact with the whole amount of matter.
Number 2 again.
Thank you for your talk. It was very interesting. One question, the bullet cluster, and given that the large dark matter masses apparently didn't interact with each other, doesn't that rule out the smoking gun measurements for dark matter?
So the probability that dark matter particles interact is assumed to be very low. So you wouldn't see it you would have events while two galaxy clusters move through each other, but they are so few that you don't see that directly in the structure. So you really have to measure individual events and the photons and the neutrinos then. So it's only very rare events that would appear there, because of course otherwise we would see it. If we had strongly interacting self-interacting dark matter, we would see that in the structures we observe.
So we have another microphone, number 5 in the back.
Hi, thanks for including me in the questions. Basically, it's a kind of advertisement for my friend physicists, which get a theory of giant primordial photons trapped by gravity. Have you heard of that?
I guess I didn't understand the theory. Can you repeat that?
It is like in the beginning of the universe, they were creating the kind of photons that are mass so giant that actually were trapped by the gravity.
I don't guess I heard about that. But maybe you come by later and we have a chat about that?
Sure, you can find his talks on Quora.com. He's called himself Piotr.
Thank you. So, number 1, please.
You showed us the slide with the experiments for detecting WIMPs.
Yes.
How far...
Into the mic. Thank you.
Sorry, it's set up for someone taller than me. How long do you think it will be before the WIMP detecting experiments actually either detect WIMPs or prove that we're not going to detect them that way? And if we don't detect them with those experiments, if we gave you a blank check, what is the experiment that you would do to help put this one to rest once and for all?
Okay, so the question when we already decided this, so I showed you experiments that are in planning currently, that are many political and technical decisions inside it when they start to run, so I cannot comment on that. Regarding experiments to decide, I mean, we try to, of course, or what is tried, I'm not in this kind of experiments, what is tried is, of course, to extend the range in all directions. But if we are not able to detect ever this kind of particles, we really have a problem, because then we don't know what to look for if it's a particle, because maybe it has some exotic kind of interaction. So we have to look deeper and deeper and up to more accuracy. So what people do now is to investigate heavily structure formation, because depending on your model of the stuff that forms the structure, structures might turn out to be a bit different, and to measure these subtleties. So we then get from a theory-driven approach to see, okay, what comes out if we assume this? Is this comparable to what we observe or not?
Number 3, please.
Yeah, thank you. I have a question to this dark energy and this accelerated expansion. I hope I can pack it into a question. We observe galaxies that are very far away, so the more far they are away, the older they are. Mm-hmm. And it is assumed that in each galaxy we have a supermassive black hole, and black holes we can say nothing about it. So one of the effects is that one of the effects is that they eat up even light, and maybe this observation we have that we interpret as dark energy.
Sorry,
maybe, yeah.
What's the question?
It's coming.
Okay,
I try. That the effect we see, that we interpret as dark energy, maybe it's a misinterpretation of what we see, and that it's an effect of the masses that masses have on light, and that there is no acceleration, and we only interpret this what we see as a Doppler effect. That we interpret it as an acceleration, but instead it's an effect of mass on light.
I am very, very sure that this is excluded by the observations we can see, because our cosmological model we developed would take this effect into consideration if it was responsible for this observation that lead us to the assumption or to the conclusion that the universe expands accelerated. So this can be excluded. Yes.
Thank you, and sorry for me being stupid. Number 4.
Hello, thank you for your talk. It's always stated that the universe is expanding. From what I understand is that there's new space created. Could it be that dark energy is the energy which is needed to create space itself?
This is basically the interpretation. So the idea is that dark energy has something we call negative pressure, in contrast to regular matter and radiation, which has a positive pressure, and this negative pressure leads to an expansion of the universe. So yes, dark energy is responsible for this accelerated expansion.
Number 2.
Have you considered that the inability to answer some questions about dark matter or dark energy indicates that we reach the boundaries of our current physical models, or rather, have you considered that that is a completely different, contradicting model of physics or mathematics that would be required to answer these questions?
So models are models because they are only subsets of what we describe, because otherwise they would be called reality. So indeed a model is never complete. The question is, when is a model contradicting something? I mean, does the standard model of particle physics contradict that there are other particles? I have a bit problems to saying they contradict. At least they are not complete. We know obviously they are not complete because we observe stuff we cannot explain. Now, the point is that to say, okay, what is likely or less likely depends absolutely on your point of view, because you have to look, okay, I have to drop an assumption we made, a general assumption, for example, like homogeneity of the universe. When I drop that, is that less strong than dropping the assumption that there are no other particles, for example, and this is hard to quantify which models are more likely or less likely, but I wouldn't call it a contradiction nowadays. I would call it incomplete.
I'm sorry, the Q&A finishes now. Please, a warm hand and a warm applause for Sarah Conrad.
Thank you.